Okay, welcome. We are continuing on here. Chapter 2 seems like a good one. Why not? So last time we talked something chemistry like, I think. So we talked a lot about significant figures last time. And we obviously talked about again how to identify significant figures and what sort of counts as a significant figure. So just again, a reminder rundown of that, which is all non-zero numbers are significant. When we have zeros, there's really, as we talked about, three types of zeros that we come across. We have the leading zeros, and those are not significant. And those again are all those zeros that come before we hit the very first non-zero number. So remember that when you look at a number, you want to sort of count how many significant figures it has. You want to always go left to right, and you don't really want to start counting until you hit that very first non-zero. So obviously these leading zeros would come before that, like something like this. All these zeros do not count because that one right there, for example, would be our very first non-zero number that we count. We also have trap zeros, captive zeros, whatever it may be. And those sort of trap zeros, those are significant. And those, again, are pretty much your zeros that find themselves between two non-zero numbers. So again, those guys will be significant. And really the last zero, which oftentimes give people a hard time, is the trailing zero. And the reason it usually gives people a hard time is for the idea that it can be significant in certain cases, but it may not be significant as well. And really, what you want to look at in terms of trying to determine whether or not it is significant is there a decimal point written in the number? So we're looking for a decimal point actually written in the number. So again, in the case of significant figures, we just don't kind of assume it's there. If it's not written, it does have to be written there to make those zeros at the end significant. So we got our 0.00400, not significant, starts counting. Zeros here at the end significant because of the decimal point that's in that number. And again, if we had something like 12,000, as we saw, I think last time as well, we have significant, significant. These are not significant because, again, there is no decimal point written in that number. So this would have two significant figures. And that also brought up an idea that we talked about last time where, again, sometimes people feel or think that the estimated digit or the uncertain digit is always the last one that's written. So as we talked about, I think towards the end, maybe last time as well, um, it is not always the last number written in a number is the uncertain or estimated digit. Very often it is, but it should always be the last significant figure that is there. So in this case, with the 12,000, the 2 is the last significant figure. And that is also where the uncertainty in this measurement lies, is within that 2. Again, not the 0 in this case. So that's also a really important thing to sort of keep track of. At the end, we got into calculations involving significant figures. And there's really a kind of two grouping of math operations that we do. We do basically, we could multiply or divide basically. And when we're either multiplying or dividing, we are looking at significant figures. That is the important thing in that type of calculation. And it's always the least number of significant figures. And the number within that calculation, if you're multiplying or if you're dividing, whichever number has the least number of significant figures would be how many significant figures your answer should have. So multiply, divide, sig figs is really what we want to look at. That's different than when we do a little adding or some subtracting. And when we add or subtract, we're actually looking at decimal places. And decimal places is actually the important thing to look at. And it's also the least in that case as well. So as we talked about last time, really your calculation that you do is only as good as your worst sort of measurement, if you will. And so when we're adding and subtracting, our worst one would be the one with the least number of decimal places. And when we're kind of multiplying or dividing, it's kind of the one with the least number of significant figures. And that's going to determine how well or good your calculation can be, is really based on that sort of last one. Remember as well that if you add and subtract, you want to go to decimal places, but that will also give you a certain number of significant figures in that number, right? So you may go to one decimal place, but you may actually end up with a number that has 3 significant figures. And then where that will be important is if you continue on, for example, with that number, you would want to then perhaps switch over to significant figures if you're going to like multiply that number by some other number as well. So if you're doing multiple steps in calculations, you want to make sure that you are doing all the operations kind of in the order. So what really determines where you will end up is the last calculation really that you do. But again, as we talked about, in order to sort of assess that correctly at the end, you also have to look at all the calculations you did up until that point, so you know really what you're looking at. So the other important thing when we're doing calculations is we want to really avoid rounding, right? Kind of till the end. We want to keep some extra digits along the way, especially if we're going to take the number and continue to use it in other calculations. We want to either keep the whole number in your calculator if you're going to kind of continue on with the calculator, or if you're going to write the number down, take a couple of extra digits more than where you should stop, and that will help avoid any type of rounding errors. Again, you do not want to round a little bit here, and then take that number, do a calculation, round a little bit here, and then keep on rounding. Again, you'll kind of move yourself probably far away from maybe the right answer and get some type of rounding error in that case. And speaking of rounding, the other important thing we talked about is no extreme rounding, right? So when you do round, we want to round things to the proper number of significant figures, but we do not want to change the meaning of the number. So we did a number of examples, I think, last time, where although we hit the right number of significant figures, like 13,000, right? 333 versus 13. Again, maybe we rounded to the right number of significant figures, but there's a very big difference in 13,000 versus 13, right? So you never want to change the meaning of that. And lastly, scientific notation, right? So any number in scientific notation, all the times 10 part, the numbers that come before the times 10 part are going to be significant, right? Any questions on any of that stuff there that we talked about last time? Okay, so let's continue on looking at some examples for maybe it's these calculations. So here again, we're doing multiple sort of calculations here together. And a reminder as well, as you see up here, the calculator obviously doesn't always give you the answer to the correct number of significant figures or anything like that. So clearly here we're multiplying. Up on top, we would actually do this first. That means we have 2 significant figures. We have 4 significant figures. That means really our answer up on top should give us something with 2 significant figures. The next thing that we would be doing is actually dividing that number that would be on top by this number that's on the bottom that has 3 significant figures. And again, here we are dividing, which means we are looking at the smallest number of significant figures, which would be really the result of the top calculation there. And that's where we should round. So 5.4 in our calculator, we would look at the next number. That is a 2. Again, that is a case where it is less than 5. So we just drop them off and we end up here with 5.4. Again, we can't put zeros, otherwise we would have too many significant figures. So in this case, we just simply drop those numbers. Questions, bless you, on that? Again, if we did this one, we're dividing. We have 3 significant figures up on top, 3 on the bottom. Again, our calculator not going to probably give us the correct number of significant figures. So this would be a case where we do have 4, but written like that, obviously, as just a 4 would have one significant figure. And in this case, we actually need 3. So here we would need to add some zeros to that answer that we see on their calculator to get the right number of significant figures. We could add as many zeros as we want here in this case. It's not going to change the meaning of the number, right? But if we add zeros incorrectly, it does change the meaning. Like if you just add those zeros with no decimal point, my 4 now just became 400. That not so good, right? So again, you got to make sure you don't change any meaning of the number. All right, so here, if we perform this here on our calculators, we will take 5 on top times 3.408. I would hit equals and then divide it by what's on the bottom, which is 2, and I would hit equals on your calculator. And on my calculator, it spits out to me something like this, 8.52. Now, let's talk a little bit about units that we see there as well. I got centimeters on top and centimeters. What do I get when I multiply both of those units together? I end up with centimeters squared, right? If you multiply the units together. On the bottom, I have 1 centimeter, right? On the bottom. That means if we just look at units, up on top, we have centimeters squared. On the bottom, I have a centimeter. These unit on top and bottom will cancel. Not both of them, just one of them basically will cancel. And that will actually leave you some centimeters left over when it's all said and done. Significant figure wise, this number has 3 significant figures, as those zeros are significant because of the decimal point. This number here's got 4 significant figures. And my number on the bottom there has 2 significant figures. That means my answer should end up at 2, which would bring me here. We're going to look at this guy. And again, in this case, we're going to drop that out there. Question on that one there. So we also want to be careful, as we'll talk about a little bit down the road here. We want to watch the units, right? We want to make sure we do end up with the proper units. Hopefully they agree. They did that really badly, by the way. They didn't end up with the proper units there on the book slide there. They should end up with actually just centimeters in that case. All right. Now adding and subtracting, we want to look at decimal places. So once again, this guy here's got 3 decimal places. We got 2 and we got 1, and we're on our calculator, we get this. That means the smallest number of decimal places is decimal place, which would give us 66.1 as our answer in this case. And by the way, that would have how many significant figures? It would have 3 significant figures, which once again would be important if you're going to take that number and do some other type of math with it, like multiplication or division. You need to switch from decimal places to significant figures in terms of figuring out where you should end up. All right, so here again, if we add these guys together on our calculator, when we do it to see what it says, it will say, I believe, 104.409. By the way, when we add, the units just stay the same. They don't square or anything like that because we're not multiplying them. So we just have milligrams as our units in this case. Here we have 3 decimal places. We have 1 decimal place, which means our answer should end up right there at 1 decimal place. And we will end up at 104.4. Here again, we're just going to drop the rest of them as that 0 is less than 5. And again, the units will just be milligrams in this case. And when you add units together or subtract units together, the units basically stay the same. They don't kind of change or anything like that. Any questions on that one? That then has how many significant figures? Does have 4 significant figures, right? They got that one right. That's good. All right. But did something right. So any questions about calculations with significant figures, how to do them? Again, a really good reminder. Doesn't always give you most of the time the answer on your calculator to the right number of significant figures. And I think I said something last time about that. Make sure you don't give an answer that the numbers just run around the page, right? 4 million numbers. So at some point you do need a round, and you should round at the end of your calculation. The next thing that we're going to talk about is really kind of dimensional analysis, also conversions and conversion factors, and how to do problem solving. And some of that's going to involve prefixes, and then we're going to talk about how to properly use prefixes. We see a lot of prefixes, and what I'm talking about is things like kilograms or kilo or centimeters, centi, and those type of things. So in chemistry, we see a lot of those prefixes used, and we want to always make sure that we use it correctly. We're going to see a table shortly that will help us figure out how to do that, and we'll talk about how to do that. Equalities are essentially two things that represent the same amount of something, but they're on different scales. So for example, if you had 100 pennies, that is the same as if you had $1, right? They both represent the same unit of money or same amount of money. They're just on different scales. You could go through the drive-through and pay with dollar bills. You could also go through the drive-through and pay with pennies, although they may not let you through the drive-through again if you come back, if you paid it all in pennies. But you can pay in either one. They both represent, in this case, obviously the same amount of money. So, especially with the metric system, we do use prefixes a lot, and we use prefixes to kind of change the meaning of the unit that we're dealing with to make it a little bit easier to kind of deal with. So, for example, 1 kilometer means that there's 1,000 meters. So kilo is kind of like 1,000, is one way that you could look at that conversion. 1 millimeter is equal to 0.001 meters, and milli is basically 1 times 10 to the minus 3. So these prefixes are used to sort of change some of the meanings of these numbers. Now, does it matter what the unit is? So when we talk about sort of prefixes and using them with units, there's kind of two terms that sometimes can be helpful. There's sort of the prefix unit and what I like to call the base unit. And the prefix unit is pretty much what it sounds like. It's the one that has like kilo in it, kilometers, kilograms, or centimeters, centigrams. It's whatever unit has the actual prefix associated with it. The base unit is the one that doesn't have any prefix associated with it. So for example, we look down there, we got 1 kilometer is 1,000 meters, right? This is the prefix unit. This is really the base unit. And the base unit in both of them are meters, right? The guy on the left there is a version of meters, and the one on the right is just meters. So the unit that basically ties both of those together are meters. Now we could do kiloliters is 1,000 liters. And as you can see here, the base unit in each of these here is liters. This is obviously our prefix unit, and that is our base unit right there. By the way, did the conversion change between those two? It didn't. It doesn't matter if it's a kilometer, a kiloliter, or the last one up there, a kilogram. Basically, the kilo part of it means that you have 1,000 of the base units in this particular case. So you could use that prefix for any type of unit. The conversion that you would use for that will be still the same, regardless of what unit that you use. So there's a bunch of different sort of prefixes that we use, and a couple of different ways that you can use them. I would say in a lot of tables, if you look them up, or a lot of ways, they will oftentimes be given to you in sort of the scientific notation sort of way. And really basic scientific notation way. Each of these, like 10 to the 12 for tera, 10 to the 6 for mega. On the bottom there, 10 to the 3 for our kilo. Those are all basically scientific notation. They're all basically, for example, 1 times 10 to the 12, 1 times 10 to the 9, 1 times 10 to the 6, 1 times 10 to the 3. Why is that important? That's important because if you need to type it into your calculator, you type it in exactly how we talked about typing in scientific notation. So if you need to use any of these with your calculator, depending on which calculator you got, as we talked about a few different types, you would type it in exactly like you're just typing in a number in scientific notation. It's basically what those mean. Here, if we kind of flip the slide here, we got a few more. And I guess we will come across a lot of centi, milli, micro, nano pops up, kilo for sure. We see a lot of, but I would say probably the big three for us would be probably kilo, centi, and milli, or kind of the ones that do pop up a lot. So for example, here, centi is 10 to the minus 2. That means 1 times 10 to the minus 2. And again, same thing here, milli, 1 times 10 to the minus 3 is basically what 10 to the minus 3 represents. So again, if you needed to punch it into your calculator, you would just punch it in like scientific notation. Now, the other really important thing with these is most of the time people screw it up when they go to this table and they do this conversion backwards almost most of the time, I would say. So what does these numbers means? How do you use it as sort of an equality? Well, this column here, where it's kind of the power 10 column on this one and the previous slide as well, that is how much there is in the base unit to one of the prefix units. So what do I mean by that? Let's take my centi here, for example. I have centimeters and I have meters, right? And I want to figure out the equality or relationship between those two. First off, let's just keep it really simple here. The base unit in each of these guys, which is the base unit here? What unit's the same in both of them? Meters, right? So meters is our base unit here. The prefix unit here is the centimeters, right? So when we go look at it and we look at a table and it says centi is 10 to the minus 2. What that means is in one of the prefix units, which is this guy, there is 10 to the minus 2 meters. And I can't tell you how many people will go to this table and go, there are 10 to the minus 2 centimeters and 1 meter and do it backwards. It's very, very common error that people make. Does it matter, again, the base unit? It doesn't. If I were doing centiliters and liters, that would mean in one of the prefix units, which is centiliters, there would be 10 to the minus 2 liters here in our base unit. Now we could do that, for example, we'll look at nano, right? If I look over here, nano is 10 to the minus 9. So if I have, say, nanometers and meters, why don't you take a second, put the correct numbers on each. All right, so let's take a look. You got a 50-50 shot at this, so hopefully we did all right, hopefully. So again, when we see the 10 to the minus 9, that is how much there is in the base unit, which means my base unit here is meters, so 10 to the minus 9, and one of the prefix units. So again, that is the proper way to do that. Question on that there. Now, you can sometimes see these conversions in sort of non-scientific notation, if you will, maybe larger numbers, and that's perfectly fine. So for example, if we look at our centimeters and meters, there is 100 centimeters in 1 meter. And that is also a correct equality as well. How you get that, by the way, is you take your 1 centimeter equals 10 to the minus 2 meters, and you divide both sides by 1 times 10 to the minus 2. That goes away. This becomes 100 centimeters is 1 meter. So that's how you get to that conversion, by the way. And again, that is the same one as well. So you could use that if you would like as well. But again, it is very common that people will sometimes mess this up. So what can we do with these equalities? And we'll kind of talk a little ahead here, kind of combine a couple of things here. Let's say, for example, we did have our centimeter there, and our centi says, again, 10 to the minus 2. And what that again means, as we just talked about, is in one of the prefix units, that is how many of the base units that we have. So this again is an equality. They both represent the exact same, in this case, amount of length or distance, however you want to think about it. And what can we really do with equalities? We really use equalities to come up with conversion factors, and we use them to basically allow us to do problem solving. So from any equality that you come across, in this case, this sort of metric to metric equality, you could always write two conversion factors. And what are conversion factors? They are simply fractions. And you just basically write two fractions. So one fraction could be 1 centimeter over 10 to the minus 2 meters. Or the other fraction could be 10 to the minus 2 meters up on top, gives us 1 centimeter. These are the two conversion factors that you could get from this equality. Any questions on that there? Now, since we're talking about this, might as well tie it together with how we use this. We use this with what is known as dimensional analysis or problem solving. It is essentially the way in chemistry that we show our work, right? And the way that we show our work is what is known as dimensional analysis. And the idea of dimensional analysis is actually a very simple idea, but it is sometimes confusing to a lot of people because it's a different way of sort of showing your work and setting up your work. So the idea of it is this: we have a certain unit that we really don't want. We want to get rid of it. And we need a way to get rid of it. And it's actually the conversion factors that we use that allow us to get rid of the unit that we don't want. And we end up with the unit that we actually do want. So that is the idea here. So the idea of dimensional analysis is a simple one, and it is the idea that opposites cancel. And that's one of the three things when you're doing dimensional analysis that you should think about, which is I have a unit here. To get rid of that unit, I need to put it in the opposite location. So when we talk about locations, because we are dealing with fractions, like you see there with our conversion factors, we basically have two locations. We have a top location and a bottom location, right? Basically the numerator and denominator. I think that's what they call that, math. It's been a while, but I think that's what they call that, top and bottom there. So we either have the unit we want to get rid of on top, which means to get rid of it, we need to put the same unit on the bottom, or we have the unit we want to get rid of on the bottom, and to get rid of it, we put it in the opposite location, which would be up on top. So always opposites cancel each other out. So for example, if we just went generically here, if I had an equality where unit A equals unit B, and I could write two conversion factors for that, where I put unit A over unit B, or unit B over unit A, right? And again, our conversion factors are really just our fractions, one unit up on top, the other on the bottom, and then flip it basically. So let's just say that I started with unit A and I wanted to get to unit B. So this is obviously a direct pathway to do that. I could go directly from unit A to unit B using my conversion factors here, right? And that's my equality. So the way you want to think about it and the way you want to show this is because dimensional analysis is all about location, 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 right? Top and bottom. That is how you want to write down everything as you're showing your work. Now, if I just have one number by itself, right? It is technically not a fraction, right? There's no top, no bottom, technically speaking, but there really is. And although we never usually write it like this, that is technically over 1, right? And in the case of dimensional analysis, that's really important because I could clearly see at this point my unit A is on top or bottom here. It is on top. Now I know I want to get rid of my unit A. So I know the main rule is opposites cancel. That means all I have to think about is putting unit A on top or bottom to get rid of it. Bottom. So that means I go to my conversion factors and I simply look for which one where unit A is on the bottom, and you will only have one choice. You will never use both conversion factors together in the same problem. Otherwise, you undid your calculation. Yeah. So you should never use both conversion factors in the same calculation, or you're basically just undoing yourself. So we could show this. I like parentheses. Some people like straight lines. It doesn't really matter. But I'm going to do a little parentheses where, again, I'm going to show it top and bottom fraction. I'm going to put my conversion factor here, unit A on the bottom, unit B up on top. First off, any questions on that there? Okay. Now that we have it set up, let's talk about math-wise what we're actually doing here. So when you set something up like this, which is how you should show your work really in chemistry, we'll talk about why that's also very helpful in just a bit as well today. But when you have it set up like this, the math is super simple. You don't have to think about what you should be doing. All you have to remember is 2 things. Anything that is up on top gets multiplied. Yeah. You could have a whole bunch of numbers up on top. Every single one of them, you multiply. Math done for you. You don't have to worry about, should I multiply? Should I divide? Should I add, subtract? By the way, if you're doing dimensional analysis, you should never add or subtract. It should only be multiplying or dividing. And everything on top always gets multiplied. What do we do on the bottom? Well, on the bottom, we do the opposite, kind of. We divide. So any number that's on the bottom gets divided. So if you set it up like this, which you should, you'll be able to see where you should take the units, where your conversion factor you should use, and the math is done for you. You just multiply everybody on top, you divide everybody on the bottom. Any questions on that? Clearly here we just have one conversion factor, but you could have multiple conversion factors that you're using in a problem. How does this help us get rid of the unit that's on top and bottom? We could just think about it like this. When units are in opposite locations, they cancel. So when you have something like unit A up on top and unit A on the bottom, they will cancel out and equal 1. It is the exact same thing if you had 4 divided by 4. What does it equal? 1. They cancel, right? Or if you had 2 divided by 2, it equals 1. They cancel each other out. So units work the same way. If you got the same unit on top and the same unit on the bottom, and you got the exact same ones, they're going to cancel each other out basically. So what we do in this case is unit A would cancel. That would leave us only unit B that we're looking for here. And that would get us really the answer we're looking for. Obviously, we would have numbers with those units. Any questions on that there? So you want to really get into that habit, as we'll talk about throughout the rest of this chapter here, of showing your work with this dimensional analysis. It is helpful in the sense, as we'll see in certain cases, you may not even have to worry about a formula. You could just take a dimensional analysis approach to it and just go, okay, I don't need those units, but I need those units. What can I use to get there? And I know when I set it up like this, math-wise, all I have to do is multiply on top, divide on the bottom. I don't have to worry about maybe rearranging a formula correctly or incorrectly. I just need to set it up that way. So it's very helpful to do that. Any questions on that there? All right, so now that we took that little detour there, let's go back to our Senti here. and kind of put it together with what we're talking about. Maybe I'll just go one more page over here. So again, we had our 1 centimeter is our 10 to the minus 2 meters. And that gives us our 2 conversion factors that we talked about, our 1 centimeter, our 10 to the minus 2 meters, our 10 to the minus 2 meters is our 1 centimeter. So let's just say, for example, we had 325 centimeters, and we wanted to know how many meters that would be. So clearly we want to think about our pathway to get there, and this prefix will allow us to directly get there. We can directly just shoot right on over there to meters in this particular case. So we're going to set it up dimensional analysis because it's never too early to start doing that. So we're going to take what was given to us, which is 325 centimeters, right? Again, it is not written as a fraction. If it helps you to visualize what's going on, throw the 1 underneath it. You don't have to if you don't want to, or you could kind of know it's on top. But if it helps you just visually see it, we can now clearly see my centimeters are up on top. That means to get rid of my centimeters, I need to put them on top or bottom? Bottom. Should I use a conversion factor on the left or the one on the right? We should use the one on the right here that we got from that table, as that is in the opposite location. That means 1 centimeter is 10 to the minus 2 meters. That is going to cancel out as one's on top, one's on the bottom. That's going to leave us meters up on top, which is the only unit left standing, which again, if you are solving for 1 unit only, it needs to be up on top by itself. It should never be on the bottom, because if you solve for it on the bottom, that is 1 over that unit and not the right answer you're probably looking for. So it has to be up on top. Now we know we set it up like this. Math-wise, what should I do on top? Multiply or divide? I should multiply. On the bottom, I should divide, right? In this case, not much to divide by on the bottom. It's 1, basically. This, again, if you're going to punch it into your calculator, that is 1 times 10 to the minus 2 using your exponent button like we talked about. And if you do all that good stuff there, 325 times 10 to the minus 2, that is going to get us 3.25 meters in this particular case. First off, any questions on that there? Now, the other nice thing about setting things up with dimensional analysis is because all you're doing is multiplying and dividing, when I'm looking for my answer, what should I look at? Significant figures or decimal places? Significant figures. So it's always significant figures in this case, since the only math you're doing is multiplying and dividing. So we do have to look at it and try to decide where we should end up. So I think we talked about last time 2 types of numbers. We have measured numbers, right, which has a certain number of significant figures. And we also have exact numbers, which can have as many significant figures as you want. So if you remember, exact numbers come from either definitions, like that, 1 centimeter is 10 to the minus 2 meters, or it comes from something that you counted, like I got 5 apples on the desk or something like that. When you're doing a calculation that involves an exact number, which will always be an exact definition when it is metric to metric conversion, which is what that one is. Or if it's English to English conversion, like 1 inch is 12, I'm sorry to say that right, 12 inches is 1 foot. They will always be exact numbers. Remember that perhaps the only time you need to worry about a kind of conversion factor that you're using is if you're doing a metric to English conversion, like 946 milliliters is a quart or something like that. So that is something that you would have to worry about. So when we think about where we should end up in terms of significant figures, this is really an exact number, which means we don't have to worry about it. That means really the only number that we have to worry about in terms of our answer is actually our original number. And our original number had how many significant figures? So our answer should have 3. Yeah, so we're good on that one. Yeah. First off, any questions on it? So let's try this one. Let's say that nano is 10 to the minus 9. And let's say you had, 4.85 times 10 to the minus 7 meters, and you want to know how many nanometers that is. Why don't you give it a go? Write the equality that you're going to use, write the conversion factors, and set it up using dimensional analysis. So take a few moments. I'll do it as well. Hopefully I made up the right number. We'll see. Okay, let's take a look. So once again, what we want to think about is if we were given this problem, we want to think here, we obviously have a prefix involved. So we want to think about what's the base unit here. The base unit is meters, right? It's in both of them. So that is the base unit here. And we want to find a way to go from obviously the base unit to the prefix unit. You would roll over to that table and you would find nano and it would say it's 10 to the minus 9. Again, we want the correct equality that's going to allow us to do that. So remember, when we see it in scientific notation from that table, that is how much there is in the base unit to one of the prefix units. So that would mean in one of the prefix units, which is a nanometer, there is 10 to the minus 9 meters, or 1 times 10 to the minus 9 meters. And that is our equality here. Any questions on that there? And again, I can't tell you how many people will do that backwards, basically. Kind of put the 10 to the minus 9 in the wrong location. Obviously, any equality you ever come across here will give you basically two conversion factors that you could use. And those two conversion factors are just the fraction. So 1 nanometer over 10 to the minus 9 meters. Or you could do 10 to the minus 9 meters over 1 nanometer. And basically, we're just, making two fractions. And one goes on top and the other, it goes on the bottom, basically. And you just kind of flip it around. These are our two conversion factors. Any questions on that there? All right, we're going to set it up here dimensional analysis way. So we're going to start with the number that was given to us, a little throwback scientific notation for good measure, right? So we got that going on. Again, here, if it helps you to do so, you don't necessarily have to, but if it helps you just to visually see it, just throw that thing over 1, basically. And now, again, we could clearly see that my meters are up on top, and that is the unit I want to get rid of. So again, opposite when we're doing dimensional analysis to get rid of it. Opposite in this case is the conversion factor here on the left, right? It has the meters on the bottom. So we'll go with, using our conversion factor, 10 to the minus 9 meters is 1 nanometer here. Once again, once we have it set up like this, we know that the meters on top and bottom will cancel since they're in opposite locations. We also know math-wise what we need to do. Up on top, we are multiplying or dividing. We're multiplying. On the bottom, we are dividing. Yeah, so it's always the same, never changes. Consistency, right? It makes it easier to remember. So it's always the same move here. Now, in this case, we could do that math. We don't really need to multiply the top one by 1 unless you like to. It shouldn't change the number. But we definitely want to make sure that we put our number here correctly in our calculator, right? Using our exponent button. So we would take 4.85, hit my exponent button, hit my negative button, and then 7. At that point, you can multiply by 1 or not. We're going to divide it by what's on the bottom. Once again, on the bottom, that is essentially 1 times 10 to the minus 9. That's how you should put it into your calculator for most people. We're going to divide by 1 times 10 to the minus 9 and hit equals. And that is going to give us 485. The only unit left up on top are nanometers. And that would give us our answer in this case. Question on that there. Answer-wise in significant figures, once again, we're multiplying and dividing, which means we should look at significant figures right here, which is my metric to metric conversion. Should I worry about it in terms of significant figures for my answer? No, it's an exact number, so we don't have to worry about it. That's exact. That means once again, we need to worry about this number. How many significant figures does that number have? It does have 3. It's written in scientific notation. Right there would be all 3 of them, yeah? That means my answer should have 3, and it does, yeah? So that is good as well. Question on that there. Yeah. No, what you would need to use, and it probably will be provided to you in this form here. We'll say like nano is 10 to the minus 9. So you need to be able to use that correctly. This is specifically like a problem, the 4.85 number. That is like a problem that would change. You don't need to memorize that number because that might change. You might have some other number. To the minus 7? No, it might change. It just happens to be the number I chose. Yeah. This will not change though. This right here, that conversion factor will not. And that's really what you need to memorize or know how to properly use and stuff like that. Other questions? Yeah. How to punch it in your calculator? Is that what you're asking? Yeah. So we're going to multiply what's on top there. So we basically have a number in scientific notation. So we want to go 4.85. Again, depending on your calculator, you do need to hit your exponent button. It is a negative exponent, so you also need to hit your change the sign negative button, and then you need to hit 7. And in this case, we really don't need to multiply it by 1 because it's not going to change the number. You then would hit the divide button to do what's on the bottom. And you would also probably put that in the same way. You would hit 1, your exponent button, your negative button, and 9, and then hit equals. Yeah, it should be in good shape, hopefully. Yeah, no problem. Other questions? And again, obviously, as we talked about when we talked about scientific notation and calculators, if you have the one with the will kind of two-tone, you do need to put parentheses around, obviously, those numbers like we talked about if you have that type of calculator. All right. So metric to metric conversions using prefixes is really important. More importantly, again, knowing how to properly use it, as people very often will kind of get them backwards. Now, another mistake that sometimes people will make when they're dealing with sort of prefix to prefix conversion, and what I mean by that is you're given a number that's in a prefix, and you also want to get an answer that's another prefix. And sometimes people will try to figure out, if I just kind of move the decimal place so many places to the right or to the left, it'll take me directly. So, for example, why don't you try one and see what you come up with? Then we'll talk about maybe how you could approach it better. If I remember what I was going to do, let's say you had 5.5 kilograms and you wanted to know how many centigrams that is. And helpful information would be that kilo from that table is 10 to the 3 and centi is 10 to the minus 2. So why don't you first give it a try and see what you come up with and set it up dimensional analysis. Think about the conversion factors that are available to you, the equalities that will allow you to do that. And then we'll talk about it here. Okay, so let's take a look, see how you're doing. So my recommendation would be this, since on an exam or a quiz, you don't have the ability to Google the direct conversion, and you probably don't know the direct conversion. But one thing that you would probably have available to you is that chart, and you have kind of the prefixing available to you. So instead of trying to figure out how to directly go from kilograms to centigrams, where you probably will make a mistake if you try to do that direct conversion, you should think about what ties those two things together, those two prefix units together. What ties those together is the base unit, right? So the base unit in this case is grams, right? Kilograms, centigrams, grams is the base unit that basically ties those together. So the logical way to get from one prefix to the next is to take it from kilograms to grams, because I could find that kilo conversion quite easily on that table. And then once you have it in grams, it's now just a simple conversion from grams to centigrams, which I could also find in that sort of table. So again, I would not try to jump it in one step because you probably will get it wrong. And this way you could always find, that pathway there. So that base unit, when you're dealing with two prefix units, is really what ties those two together. So to do that, we do need some equalities that are appropriate here. So clearly we're going from kilograms to grams. So I know when I look at this here, the 10 to the 3, that means in 1 kilogram, I got 10 to the 3 grams, which is my base unit. That's my equality there. And from that equality, that's going to give me two available conversion factors that I could actually use in this calculation. I could use it as 1 kilogram up on top and 10 to the 3 grams on the bottom. Or I could flip it around, 10 to the 3 grams up on top, 1 kilogram on the bottom. And these are my two available conversion factors. Once again, you're not going to use them both. You're just going to use whichever one is going to get you there. While we're at it here, we're going to go from grams to centigrams in the second step. So once again, when I look at that table and I see centi is 10 to the minus 2, that tells me equality-wise in 1 centigram, that is 10 to the minus 2 grams. Again, that's going to be my equality. That's going to also yield me two possible conversion factors that I could use, which is 1 centigram up on top, 10 to the minus 2 grams on the bottom, or just flip it around, 10 to the minus 2 grams up on top, 1 centigram on the bottom, being my conversion factors here. First off, any questions so far, how I got everything? No. All right, now that I got everything I need, I just kind of has to do the problem, I suppose. So let us do the problem here, which is we're going to start with what was given to us, which in this case is 5.5 kilograms. And I know I do not want the kilograms anymore. So once again, if it helps you, just put the 1 underneath it to start. And now again, I could clearly see my kilograms are up on top. I need to get rid of them. Dimensional analysis tells me opposite does that. So should I use the conversion factor up here on the left or on the right? Which one should I use? I should use the one on the right, as that puts kilograms in the opposite location, which is on the bottom. So we're going to do our little setup here showing that 1 kilogram on the bottom, 10 to the 3 grams up on top. If I stop this calculation right at this point, what units am I in? I am in grams because the kilograms on top will divide out the kilograms on the bottom, and I have grams. The benefit of doing that is I don't have to think about it too much because I could clearly see grams are where now? On top, which means if I want to get rid of them, I need to put them on. Yeah, so which conversion factor should I use on the bottom there? Left or right? I should use the one on the left. Yeah, that has the grams in the opposite location. And I could just continue on. You could get an answer if you wanted to at that point, or you could just continue on with the calculation since you need to do it anyways. So to do that, we're still just going to do opposite. Grams are on top. I need them on the bottom. 10 to the minus 2 grams on the bottom, 1 centigram on top. Grams on top, grams on the bottom. Cancel each other out. Yeah. I am now left with only one unit left, which is up on top, and that is centigrams. And that's good because that's what I'm looking for, right? Now, because we are professionals at this, right? I already know math-wise what I should do. What should I do up on top? Everything should get multiplied, right? So everything up on top gets multiplied. On the bottom, everything should get divided. Yep. And again, we want to make sure that we put our numbers in properly in scientific notation. So let's do that. So we're going to go up on top, 5.5. We're going to multiply it by basically 1 times 10 to the 3. So we'll multiply that by 1 times 10 to the 3. And by the way, the next one is 1. You don't really need to multiply it by 1. If you like to, you can, but you don't have to. What you should always do when you're doing something like this is once you get to the top, you can multiply as many numbers as you like. At the end of that calculation up on top, make sure you hit the equal sign. And then you should come and divide by the very first one here, which happens to be a 1, which you really don't need to. But make sure you hit the equal sign after you divide it by 1. And then you should divide it by the next number, which is 1 times 10 to the minus 2. And make sure you hit the equal sign. So we'll divide it by 1 times 10 to the minus 2. That is going to give me on my calculator here 550,000 centigrams. That's a big number. Does it make sense? It does, because centi is a smaller value, right, than kilo, right? Kilo is a larger value. Centi is a smaller. So you have a lot more of the smaller guys to make up the big guy, right? So that does make sense. Let's talk significant figures. That is metric to metric. Do I need to worry about it? I do not. That's an exact number. That's also metric to metric, which means I do not need to worry about it. That would be the only one I need to worry about, which means my answer should have how many significant figures? 2. Does my answer have 2 significant figures? It does, actually, the way I wrote it. You could also do scientific notation if you wanted to. You could have went 1, 2, 3, 4, 5, 5.5 times 10 to the 5 centigrams. Why did I drop the zeros there when I wrote in scientific notation? Right. If I left the zeros in scientific notation and wrote it, I would then have like however many significant figures that is, 6 or so, and that would be too many. Questions on that there? Okay, we're going to continue on here. Any questions so far? So we kind of jumped ahead a little bit and kind of put things together, and we'll take a look at some more examples here. But again, I would highly recommend you get familiar with how to properly use those prefixes. Like I said, kilo, centi, milli, we do come across a lot here in chemistry, and trying to use it correctly is really important. Also, getting in a habit of setting up your work like this with dimensional analysis, which is technically how you show your work. Hopefully you can start seeing some of the benefits here of doing it this way, because frankly, it takes a lot of the thinking out of it in some cases, right? You just got to remember opposites, multiply the top, divide the bottom. It really does sort of simplify a lot of things. And as we get going, you'll see, like I said before, there are certain cases where maybe, if you can't remember a formula or something like that, you could just think of it unit wise, dimensional analysis wise, and you could almost probably figure out, how to solve for something just by, again, getting rid of units you don't want and kind of keeping the units that you do. Any questions on that there? All right. So let us continue on here. So let's take a look at a few of these here. We kind of covered some of these as we went through it. But 1,000 meters is equal to 1 kilometer, right? That is basically the conversion. And again, that is essentially what 1 kilometer is 10 to the 3 meters. 10 to the 3 is 1 times 10 to the 3, which is 1,000 basically, right? So that is, again, where that number comes from. 1.1 times 10 to the minus 6 grams to the minus 6 is the micro conversion. And I don't know, your book kind of goes back and forth on micro. The symbol, they use this for micrograms sometimes. The real symbol that most people use for micrograms is this kind of like U looking thing. Micro is that U type of looking guy. So I probably will use this symbol because other than your book, I haven't seen it too much, that conversion sort of used or that abbreviation used. But they do kind of bounce sometimes back and forth between MC for micro and the little micro symbol. So just keep that in mind. 0.1 liters is basically 1 times 10 to the minus 1, which is our deci conversion that we see on that list there. All right, so length equalities, again, it works the same way as we've been talking about. It really doesn't matter what the base unit is. It's really the prefix part of it that's important. It could be grams, like we saw there, kilograms. It could be kilometers, could be kiloliters. It's really the same conversion. And sometimes people think it's something very different when they see like a different base unit. But again, just remember that if it's that same prefix unit, it's the same one that you use, you know. So for example, you could use it either way, but you know, there's 1,000 milliliters is 1 liter, for example. And then when somebody's asked, you know, how many millimeters would there be in a meter, they're not really sure, but it's the same conversion. There's 1,000 millimeters in 1 meter and so forth. So again, doesn't matter the base unit, the prefix basically is what it is. And you could apply it to any sort of base unit that you want, and it works the same way. Now, volume, deciliters, liters, again, I would say, as we might have talked about last time, we definitely should know that conversion there. That is one that does pop up all the time. So that's the best one to probably remember in terms of volume. There's 1,000 milliliters in 1 liter. The reason that does pop up a lot is, for example, in the lab, you usually will measure your volume in milliliters, but a lot of times when you do some type of calculation in chemistry, the volume oftentimes has to be in liters. So kind of going back and forth from liters to milliliters is a conversion that you use a lot. And once again, it doesn't matter if you use the kind of power to 10 or scientific notation version of it, or if you just use kind of regular numbers. This is still an equality, and you could still get two conversion factors from it. 1 liter over 1,000 milliliters, or 1,000 milliliters over 1 liter. So again, it doesn't matter if you use the scientific notation version of it, you use sort of the whole number version of it. If it's an equality, you could lay up two conversion factors. You know, we talked about 12 inches is 1 foot. You could write 12 inches over 1 foot, or 1 foot over 12 inches. Those are, again, the two conversion factors that you could get from that equality. And again, it doesn't really matter what the equality is. You could always get two conversion factors that you could use in a dimensional analysis sort of calculation. We also talked about other volume relationship equalities that are important. 1 cubic centimeter is equal to 1 milliliter. It is a 1-to-1 conversion between that. Although most people don't show this part of the calculation, but basically you still could get two conversion factors. 1 cubic centimeter over 1 milliliter, or 1 milliliter is 1 cubic centimeter. So it does not really matter what the equality is. You can get a conversion factor, really two conversion factors available to you to use. We also talked about it in medicine, right? They use cc a lot of times for cubic centimeters, which is a milliliter. Again, usually if you look at a needle or something like that, if you're going to give somebody some medicine, it is oftentimes in cc's as to how much you give them. So again, there's our relationship there of all three of those guys there. Now, mass equalities, as we've been talking about, we've kind of touched upon some of these. Again, if you like kind of remembering the bigger numbers rather than sort of the scientific notation, you know, it's all good if you want to do that. If there's one where you can't really figure out the regular number, you just, again, divide the scientific notation by itself and take 1 over it, and it will convert it into what you need. All right, so let's talk about these units, right? Which one is larger, millimeters or centimeters? Which one's larger? It is centimeters, right? That's on the bottom of the ruler with numbers. And the millimeters are the little guys on the bottom there with no numbers between them. Kilograms, centigrams, kilograms, deciliter, microliter. See, they used the symbol there. That is deci, right? And micrograms and milligrams. Even I had to take a moment there. We think, oh, that kind of looks the same as well. So that is, again, milligrams there, are micrograms and milligrams. So milligrams would be the correct one there in terms of which one's larger. So again, it's important to understand, you know, sort of which one is larger, which one is smaller as you're moving through the prefixes, going one way or the other. So a couple of these other ones that we sort of touched upon, 1,000 meters, again, is a kilometer, right? So that should be our kilometer. Again, if you're not sure what this is, you can kind of throw in scientific notation. That's like 10 to the minus 2. That looks like a centi type of conversion, perhaps. And that would be our centimeters in that case, if you kind of convert that into the scientific notation part of it. 1 kilogram is 1,000 grams. And I'm not sure on your hand if there was still a typo on this one. There was. It should be this guy there. Should be the correct conversion between it. I think it had number 2, which was the same thing as what the original number was. So it's not a 1-to-1 conversion, but it should be that guy there. All right. We've kind of touched upon this earlier here, so we're now going to officially talk about, again, conversion factors and how to write them and use them. Hopefully you're starting to get the hang of it. As we talked about, we could have equalities, and there really is sort of 3 types of equalities that we come across, and they're really based on the different units that we have. So we have obviously our metric to metric conversion, and again, that is going to be, as we've been talking about, considered an exact number. We also have our English to English conversion or equality, and that also would be considered an exact number. And then we obviously have our kind of metric to English conversions, our equalities, and that is the one and really the only sort of conversion that if you use it in a problem, you really should look at the significant figures and include them or think about them as you're thinking about your answer. So typically speaking, if you do come across a metric to English sort of conversion, there oftentimes will be one part of that equality or conversion that is a 1. And that is the number you shouldn't look at. You should look at the other one that looks more like a real number other than 1. And in this case, if we had to count significant figures, this guy would have 3 significant figures here. So this guy would have 3 significant figures based off of that number. So 9 times out of 10, if you're doing some dimensional analysis, you're doing some conversions, you're using some conversion factors, you could almost go autopilot and go, that's a conversion factor, I don't need to worry about it. And I'm just going to look at that first number. And a lot of times, I won't say 100% of the time, but 98% of the time, that original number that you started with, if all you're doing is converting it to some other unit, a lot of times that is the correct significant figures that your answer should have. It is not always that, especially if you come across a metric to English conversion that you're using. You do have to take that into account. But most of the time, any conversion factor, you could almost not worry too much about it. But this is the one place where you do have to kind of worry about it if you're kind of crossing over from metric to English. There are a couple of those, as we will see, which you don't have to worry about that are considered exact ones, even if they are metric to English, but most of them you do have to worry about it. We see it on food labels, right? We see, you know, kind of like the English or US units, and in parentheses, right, we see grams, right? If you watch a baking show or something like that from people from England and stuff like that, they measure things out with a scale and how many grams they put in there, right? Rather than cups and all that kind of stuff like we do here. So we see it on food labels. We see it like we talked about, that kind of English and metric differences. So here again, this are going to be exact conversions, each of these. Again, we have metric to metric. We got English to English. We obviously have exact time there. So none of those, if we use them in a conversion factor, are an actual problem, would we have to consider in terms of our answer. We would just sort of ignore it in terms of the answer and significant figures. These are all equalities here. And they all would yield you, as we've been doing, for example, 2 conversion factors that you could use, which again is just our 2 fractions and stuff like that. Here, these are all English to English. And here we are now crossing over. So when we cross over here to English to metric, we do have to take into account, like I said, the significant figures. I will say a lot of times, even if you need to take into account, for example, these guys in terms of their significant figures, still a lot of times, not again 100% of times, you're still going to kind of default to that first number. It kind of is usually the smallest. Once again, in each of these cases, we would look at the number that's actually a number here to determine significant figures. So each of these guys would basically have 3 significant figures as we look here. The one sort of metric to English conversion that is considered an exact number is the one that we see here, and that is 1 inch is 2.54 centimeters. And sometimes people write exactly next to it to emphasize that that is an exact conversion. So if you're using that conversion in a calculation, the 1 inch is 2.54 centimeters. You don't have to worry about it. You could consider it an exact conversion. But pretty much all other metric to English conversions, which are all these are metric to English, you do have to look at the significant figures when you're doing a calculation. And as we just talked about, when we use dimensional analysis, we're just multiplying and dividing. So that's all significant figures is what you want to look at in terms of your answer as to where you should end up. So conversion factors, as we've talked about and did some examples, again, it's a fraction, numerator and denominator. And you really just want to keep it simple like we were doing in those examples. Top, bottom, opposites cancel, right? So that is really the important part of it. Here, 1 hour is 60 minutes, gives us 2 conversion factors, 60 minutes over 1 hour, or you could use 1 hour over 60 minutes. Again, you won't use both of them in an actual problem. Now, there's also sometimes conversion factors that are given to you in the problem, for example, and they're not really exact conversions. And when you have some type of conversion factor sort of given to you in the problem, you do need to typically look at the significant figures for those. For example, if you were told you're driving 55 miles per hour, right? That basically means that you could go 55 miles in 1 hour, or in 1 hour, you could go 55 miles. These are the 2 conversion factors that you could get. And if you were to use that in a calculation, you would have to look at the 55 and count it as 2 sig figs and take that into account. So sometimes in problems, they kind of give you something that you could use as a conversion factor. And if that's the case, then that's also another situation where you should probably look at the significant figures because it's not an exact conversion, right? People don't always drive 55 miles per hour, right? Perhaps they drive a little faster than that or maybe a little slower than that, but they're not always moving that way. So that is something that's kind of specific for the problem you're dealing with, which means that you do need to take it into account in terms of significant figures. Here's a nice little table of some conversions. And once again, pretty much anything in this column here that you use, since it's metric to metric, would be considered exact. Anything in this one, which is US or English to English, would be considered exact. Anything in this column, you need to look at, except for obviously our 1 inch is 2.54 centimeters. Everybody else you do need to look at and take those significant figures into account. I would say most of these would probably be provided for you, but you need to be able to use them correctly, I guess is the way to say that. Some things may not be provided for you. So again, some things hopefully you know, right? So again, how many seconds in a minute, right? And minutes in an hour, and hours in a day. 24. There you go. So that might not be provided for you. So, make sure you know at least something like that, I hope. So any of these guys, once again, we could pull any of these guys out. We could take 3 feet equals 1 yard. And that would mean that we would have 2 conversion factors, right? We could write 3 feet over 1 yard. Our 1 yard is 3 feet, right? So, for example, if we wanted to know, Somebody ran the kickoff back 98.5 yards, right? And we wanted to know how many inches did they go? Why don't you do that? I'll do it as well. So find your equalities that's going to get you there. Find your conversion factor, set it up with dimensional analysis, and see what you get. Okay, so let's take a look. So first off, we got 98.5 yards, and we want to know how many inches. So the first thing that you want to think about is how can you get there? And when you're doing conversions and just sort of problem solving, there can be multiple ways to get to the same answer depending on sort of what path you choose in terms of conversions and equalities that you use. So you want to think about maybe the easiest path to get there. So for example, obviously I have some feet and yards up here already. So that's going to take me from yards to feet, right? So that would be like perhaps my first step. And then obviously if I'm in feet and I need to go to inches, I should also know, right, there's 12 inches in 1 foot. And that would take me from feet to inches. And that would allow me really to get to where I want to be. So again, you might have took a different path as long as you chose a legit conversion, not one that you just made up yourself. You know, it should get you to the right answer. So let's kind of work through it. We have our 3 feet equals 1 yard. That again is our equality. That's going to give us 2 possible conversion factors that we could use. And then we have our 12 inches equals 1 foot. Again, another equality that gives us 2 possible conversion factors. And as we've been doing, again, you should not use both of them in the same calculation, but you just want to pick whichever one's going to work for you. So we'll start with our first number there, which is 98.5 yards. Once again, we want to do a little dimensional analysis. So to help us out, maybe we put it over 1. That again makes our choosing hopefully easy, right? Because yards is up on top, which means I want to get rid of it, and that needs to go in the opposite location. So that's going to be conversion factor here on the left is going to do that. And we'll set up our dimensional analysis so we can actually see those units canceling. We're going to go 1 yard on the bottom and 3 feet up on top. If I stop the calculation right at this point, the yards up on top will cancel the yards on the bottom. I am left with feet there up on top, right? And that also makes my next decision pretty easy, right? Because I want to get rid of feet. It is up on top. It needs to go on the bottom. So conversion factor there on the left or right should I use? I am going to use the one on the left where we have it in the opposite location. And we're going to do a little 1 foot is 12 inches. Feet up on top, feet on the bottom are going to cancel. We are now ready to get our answer. Because we set it up like this with dimensional analysis, we should also remember up on top gets multiplied. Yes, everything up on top gets multiplied, and everything on the bottom gets divided, right? So simple 2 process there, right? Multiply, divide, top multiply, bottom divide. Nothing too much to worry about. We're going to punch this in. We're going to go 98.5. We're going to times it by 3. We're going to times it by 12. We're going to hit an equals, maybe. And in this case, we really don't have to divide anything on the bottom because they're all ones. If you like to, you can. Nothing's going to change, but there's really nothing on the bottom there to divide. That's going to give us on our calculator 3,546 inches, which is our last unit up on top that stands that has not canceled out. First off, question on the conversion factors, the equalities, the setup, the math. All right, we do want to give our answer right to the proper sig figs, and I already know it should be sig figs because I'm dimensional analyzing over here, which means I'm multiplying and dividing, which means it should always be sig figs I should be interested in at this point. Do I need to worry about this conversion factor? I do not. That's English to English. No problem there. We do not need to worry about that one either. That means here the only number left is the original number, which has how many significant figures? That means my answer should have my third significant figure in my answer is which number? It is the 4. I then should look at the number next to it, right? And I should round up, right? So 355 0, right? We do need the 0 there, right? Inches. Why do I need the 0 there? Because 355 is very different than 3,000 and 3,500, right? So very different numbers. So again, we want to be really careful not to over round, right? Although you might hit the right significant figures, you change the meaning of the number. So we don't want to do that. Any questions on that particular one there? All right, while we're here, let's just do one more, just a good practice. I'm just gonna erase everything on there. That didn't work. It's not gonna work because I already did that, huh? All right, so we'll just do this. Let's just say we drank I don't know, how about 6 cups of coffee? Hopefully not in the same day. How many milliliters would that be, perhaps? So again, think about a pathway that will get you there. And again, don't try that at home. And one day, that's probably a lot of coffee, I imagine. Okay, so let's see how you're doing. So once again, we want to find a pathway that's going to take us from our first unit to our final unit. Maybe 1 step, maybe 2 steps, 3 steps. Usually I wouldn't say it's more than 4 steps probably in most cases. But 2 to 3 usually is the way to go. So I'm going to look here and I can see, for example, cups to quarts will get me moving perhaps in the right direction. And once I have it in quarts, I can see over here a direct conversion from quarts to milliliters, which will basically take me the rest of the way. Once again, you might have took a different approach or different pathway to get there. If you chose, like I said before, sort of legitimate conversions, you should end up in the same place. So it's okay. It doesn't necessarily have to be done one way or the other. But I'm going to go with that route there. And I'm going to try to remember what I chose there. So it was 6 cups of coffee, I think, right? So 6 cups of coffee. And we want to know how many milliliters. So we have 4 cups in a quart as an equality. And we have 946 milliliters in 1 quart as also an equality that will again get us there. So our pathway there is cups to quarts, and we're going to use kind of quarts to tie those two together. We're going to kind of go in that path. So once again, if it's helpful, you can lay up all your possible conversion factors, which once again, you probably won't use obviously all of them. So we could have 4 cups over a quart, or 1 quart is 4 cups for some conversion factors here. We also could have for our second one there 946 milliliters over 1 quart, or again 1 quart over 946 milliliters. So once again here we have our conversion factors. We have a pathway to get us to where we're trying to end up. So all that's left is actually do the calculation here. So let us do that. We're going to start with our 6 cups. Once again, going to take our dimensional analysis approach. Going to pop that over 1. Again, making it pretty easy to determine. I should use in terms of these conversion factors here, the one on the left or the one on the right, which one's going to work? We want the one on the right, opposite. Cups are up on top. Cups need to go on the bottom. So again, we're going to set it up so we can see that. That is the 4 cups equals 1 quart. Once again, if we stop right now, we will end up with quarts as our units. You can absolutely, if you wanted to, for example, if you're doing multiple conversions in a row, you could get an answer at this point. I would obviously recommend not rounding if you do that, because you definitely will start moving yourself sort of off. So you probably don't want to round. If you do want to get an answer, you don't have to get an answer, because the nice thing about setting it up like this, once again, we could see quarts here are up on top, which means opposite to cancel. That's going to move us to our conversion factor here on the left to do that. And we will put that in there. And we got 1 quart on the bottom, 946 milliliters up on top. Quarts on top, quarts on the bottom will cancel at this point. We know we are done because we're looking for 1 unit. And our 1 unit's up there on top by itself. So we're good. We're at the end of the road here. First off, any questions so far on the setup, the conversion factors, any of those things there? All right, so we are again professionals here, so we clearly know what we should be doing, and we're going to multiply whatever we got going on up on top, and we're going to come back and divide by what we got on the bottom. Once again, here, you don't necessarily have to do the ones if you don't want to. Maybe you shouldn't, so you don't mess anything up. But we're going to take basically 6 times 946. And that's basically everything that we need to multiply up on top. Again, you do want to hit the equal sign on your calculator, trust me. We then want to come to what's on the bottom there and divide. And it's really only the 4 that we got there. So we're going to hit our divide and by 4 and hit the equals. And that's going to give us 1,419 milliliters of coffee that was drank. Now we want to think about significant figures, right? So do I need to worry about this conversion factor? The answer is yes. That is a metric to English conversion, which means I do need to worry about it. Which number should I look at, the 946 or the 1? Yeah, 946, which has how many significant figures? 3. So again, metric to English here, we do need to look at. Just write the classic look next to that, right? So we want to look at that. How about the quarts to cups? Do we need to worry about that? We don't. That's exact, so we're good on that. How about the original number? Do we need to look at that one? We do. That has how many significant figures? That means since all we did here is multiply and divide, my answer should have how many significant figures? Should have 2, which means my answer should end up at 1,400 milliliters. Yes. Once again, 14 is be great, but you probably drank more than that. Yeah. So 14 is a very big difference in 1,400. So again, we do not want to over round here and change the meaning of it. You also, once again, if you wanted to, could do a little scientific notation if you like, 1, 2, 3. And once again, if you did write in scientific notation, you do need to write it like that, because that will give you 2 significant figures. Question on conversions, equalities, dimensional analysis, which is really what we're doing. Yes. What? Say again. Why is which one not an exact number? I'm sorry. No, this conversion factor here is not considered an exact number, because it's a conversion factor that goes from metric to English, the 2 different unit scales. This one in the middle is considered an exact number because it's basically English to English, and you don't have to worry about it. And this one is the original number, which we do. So this was the answer we got on our calculator. And because of that, we had to look at this conversion factor and the significant figures here with the original number. And because we're multiplying and dividing, we follow the rules for multiplying and dividing, which is we need the least number of significant figures. And that would take us to 1400, which should be the correct number of significant figures. Or if you want to write in scientific notation, you could write it like that, which would give us 2 significant figures. Other questions on that? All right, well, that feels like a good